All right, 10.3. So just some definitions to start off with. We need to look at non-decreasing partial sums. For a specific reason, we need this for the next theorem that we're going to jump into. So a non-decreasing partial sum, I hope it's pretty obvious that what this basically means is that when you are finding the partial sums, they're always either staying the same or they're increasing. There's another way to say this, i.e., this means that your sequence terms for your series are all non-negative, or zeros or positive, basically. So basically what we need is we need a series where we're only adding positive terms to it the entire time. If that's the case, we're going to have a special test that we'll get to in just a minute. And even more so, we can take this even further. If we have an upper bound on the partial sums, then by the monotonic boundedness theorem, we have the series converges. So this isn't like a real test. This is just kind of a statement that we're going to use for the official test that we're going to have. But if we do have non-decreasing partial sums and then we have an upper bound to that, if you remember back from section 1, that means that it's monotonic because it's non-decreasing and it's bounded. So then by that theorem, we have that the sequence of partial sums converge. And if the sequence of partial sums converge, that means the series itself converges. Before we jump into the main theorem of this section, I do want to show you one example called the harmonic series. I think I even used this as an example in a few videos ago, but this is the harmonic series. If we look at the series as n goes from 1 to infinity of just 1 over n. So we kind of talked about this a little bit when we were doing the nth term test. If we write out the terms, it's going to be 1 plus 1/2 plus 1/3 plus 1/4. The sequence terms themselves are going to 0. But remember, just because the sequence terms go to 0 does not mean that the series converges. In fact, this is an example of a series that diverges. All right. And I can kind of show you why it diverges just inherently, and then we're going to use this big theorem that we're going to come up with here in just a second to see another reason why it diverges. To show you why it diverges just kind of explicitly, I need to write out a few terms here. So I'm going to go all the way to 1/16. I'm going to skip around a little bit. We're here, need a little bit more, 1/9 plus 1/10, and I'm just going to do dot 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 to 1/16. And then, of course, it goes even further than that. Okay, what we're going to do is we're going to group some of these terms together. The one I'm going to leave on its own. I guess I'll put parentheses around it. Oh, jeez. Sorry, I just had a stroke on the keyboards there. The 1/2 I'm going to leave alone. The 1/3 and the 1/4 I'm going to combine together. The 1/5 all the way up to the 1/8 I'm going to combine together. And then the 1/9 all the way up to the 1/16 I'm going to combine together. And then we'll just do the dot 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 after this. All right, the reason we're combining these together is because we're trying to talk about the boundedness of the partial sums. If we look at these parentheses, every single one of these parentheses have an internal sum that's more than 1/2. So each of the parentheses have a sum that is greater than 1/2. What this means, and you could keep doing this, by the way, right? You can keep finding groups of things that are bigger than 1/2. What this means is that there can't be an upper bound. If you do choose an upper bound, say you choose, 100, that just means you would have to find 200 of these groups, and you're already bigger than that upper bound. Every single upper bound that you pick, I can group stuff together to show you that we're actually bigger than that upper bound. Therefore, it's not really an upper bound. Thus, this means the harmonic series diverges. It diverges because the sequence of partial sums does not have an upper bound to it, and it's monotonic. Okay, so that's just one way of seeing it, not the way that I would expect you guys to do it. Instead, we're going to use something called the integral test. So the integral test, let me just write it all out. Let there be a sequence, a sub n, of positive terms. Remember, we had to have them positive terms. Suppose that we also are going to define a function for each of these sequence terms. So we did this back in section 1 as well. Most of the times for these sequences, we can find a function with the same index. So where f is continuous, positive decreasing function of x for all x greater than or equal to n. So this capital N is important. What this is saying is that this doesn't always have to be true. You only have to have a function that matches the sequence values after a certain index value, and it doesn't matter what that index value is. All right, so if all of that stuff is true, then the series as n starts from that index to infinity of these sequence terms, and the integral, so this is going to be the integral from capital N to infinity over the function of n, dn, both converge or both diverge. All right, so we'll go through this again. Let there be a sequence of positive terms. We're going to look at the series of that in a second. Suppose that each of these sequence values is equal to some function where f is continuous, positive, and decreasing for all, this should be an x, I guess, for all x values that are beyond the index values. Okay, then if that's the case, the series from that starting point to infinity and the integral from that same starting point to infinity are going to be twins. If one of them converges, the other one converge. If one of them diverges, the other one diverge. Please note, though, this, I can't do a, there we go. This does not mean they converge to the same value. So just because one of them converges, it means the others converge, doesn't mean that they converge to the same thing. It just means that they converge in general. Okay, I do have the proof for this, but I don't want to make a video for the proof. It's in the book. I would recommend that you look through that just because I think it is, I think it's pretty interesting and pretty exciting. It's using Riemann rectangles to do it. So let's look at the harmonic series in going from 1 to infinity of 1 over n. Let's use this integral test to prove that this thing really does diverge. To do that, we're going to be looking at the integral. Now, before you get started on these and you're using the integral test, you do have to make sure that all of the prerequisites hold. You have to have the f is continuous. 1 over n is continuous in the positive half of the x-axis. They're all positive numbers, and it's decreasing, right? As my n's get larger, these values do decrease. So what we're going to do is we're going to integrate from 1 to infinity of my function, and I'll write it as 1 over x dx. Okay, not a hard integral to do. That has antiderivative natural log x, and then we're evaluating this from 1 to infinity. All right, so it's not obvious that this diverges itself. But if you look at the natural log graph, or if you just plug really big numbers into the natural log, you should see that the natural log of infinity blows up to infinity. The natural log of 1 is just 0. So in other words, this still goes to infinity, which means that the integral, thus the integral diverges, which by the integral test means the series also diverges. Okay, so what the integral test says is that if you have a series if it follows all of those prerequisites, positive numbers, decreasing, continuous, if you integrate over the sequence as a function, if the integral diverges, the series diverges. If the integral converges, then the series converges. All right, so let's look at a couple more examples. This next example is a very important example. It's called the P series. So this P series is going to be the infinite series of 1 over n to the power p. Basically what we want here is we want to figure out for what values of p is this going to converge. And we can do that using the integral test. So again, using integral test, let's look at the integral from 1 to infinity of 1 over x to the p power. And keep in mind that p is just a constant. We're just trying to figure out what that constant needs to be for this to converge. So we can find the antiderivative for that. So this is going to be, you can think of that as being x to the negative p. So we're going to subtract 1 away from negative p and then divide. So it's going to be, I guess negative, how am I going to do this? Let's do 1 over negative p minus 1, x to the negative p minus 1. All right, so this is the antiderivative for 1 over x to the p. We're going to do the same thing. We're going to take that and we're going to evaluate that between infinity and 1. If I plug infinity into this, we have to be careful. It all depends on what that value p is. So let's kind of rewrite this a little bit in a way that makes a little bit more sense for us. And to do that, I'm going to think about it more like a limit. So this is going to be the limit as b goes to infinity. Let me get the limit that has the subscript to it. So the limit as b goes to infinity of, and then on the inside here, we're basically just going to rewrite this a little bit. I'm going to take the negative sign out of it and write that front part as 1 over 1 minus p. Oh, I think I did this part wrong, didn't I? Sorry, this was supposed to be plus 1 on top and bottom. All right, if I messed that up, sorry about that, but we add 1 to the exponent and then divide. So it's x to the negative p, we're going to add 1, divide, and then that negative p plus 1 up top there. That makes more sense. All right, so I'm taking a negative out of the bottom, so I'm writing that as 1 over 1 minus p out in front here, and that's going to leave us with just that x to the negative p plus 1, but it's going to be a negative sign. I'm going to take that negative sign and just pull it all the way out of the integral instead, though. All right, so x to the negative p plus 1. This is still going from 1, but now it's going up to b. So this is rewriting that limit the way that we used to write it back in chapter 8. All right, now we still have the limit as b goes to infinity. I'm going to go ahead and pull that constant out in front as well. We don't need this 1 over 1 minus p, so that's going to come out front. In the inside, we're going to go ahead and evaluate the x from b to 1. So if I plug b into this, I'm just going to get b to that negative p plus 1. That's going to be, if I plug 1 into that, I'm going to have a 0 as the exponent, so it's just going to be minus 1. Put these in brackets. Okay, now let's talk about what happens as b goes to infinity. So as b goes to infinity here, it depends on what the value p is. If this ends up being negative up top, then it's going to blow up to infinity. However, or sorry, the other way around. If this ends up being negative up top, then this term goes to 0, which is good. That means it converges. If this term ends up being positive up top, that means that this is going to blow up to be positive infinity. In other words, what this statement is saying here and what's important to you is that this converges as long as p is greater than 1. Okay, so in the end here, the p series, this series, 1 over n to the p, converges as long as p is greater than 1. So we already saw the harmonic series. The harmonic series was when the p was equal to 1. That diverged. But as long as the p is just barely bigger than 1, or I guess anything bigger than 1, then this is going to converge. Okay, so I'm going to make one more video here for this section.